factorization of constant depth circuits.
Okay, I think I should start a timer, otherwise I'll lose track completely. Okay, thank you everyone for staying till the last talk. So if you paid attention in Robert and Shantanu's talks, which were great, that will be good for me because some of my prereqs were covered there. And in case you ended up taking a nap, then I hope you're fresh now for this talk. Okay, so yeah, the talk is going to be about the same objects that were covered in their talks, which are constant depth arithmetic circuits. And we are going to try and factorize these circuits, which means factorize the polynomials deterministically. So just a very quick warm-up. Our main objects of study are going to be polynomials over rationals, let's assume that. And okay, we are trying to answer how do we factorize polynomials. Multivariate polynomials, that's what we are interested in. But first of all, how do you factorize univariate polynomials over rationals? Answers? You can use an algorithm by Lovász, Lenstra, and Lenstra, which goes through some lattice-based machinery. But what about bivariate and multivariate polynomials? And like Shantanu said, the question of representation here is important because how do you even represent them if you're trying to talk of efficient algorithms for factorizing them? And our model is going to be arithmetic circuits. I don't have Tixi diagrams, and thankfully they had great diagrams. And the size of the circuit is going to be number of wires, and the depth of the circuit is just going to be the longest path from leaf to root. Okay, and when we say circuit class C, just think of it as applying some restriction on the resources you are allowed to use, that polynomial size, constant depth, and so on. Okay. And so these are results from the 80s, where we knew efficient randomized algorithms for computing factors of polynomials that are given by small arithmetic circuits, right? So these had no depth restrictions. They're not formulas. They're just the most general class of efficient circuits. And here we had efficient randomized algorithms. In particular, note that there is both a structural result and an algorithmic result here, which is that because you're doing these things efficiently, your circuit sizes are going to be small for the factors. And moreover, you are computing these factors efficiently. And there are many other there have been many other restricted results on polynomial factorization. There's a great survey of Michael Forbes and Amish Vilka. And there are also many interesting applications in coding theory, hardness versus randomness, and so on. Okay, just a quick note again on this distinction between a structural result and an algorithmic result. A structural result just says that if a polynomial has a representation in a circuit class C, then so do its factors. An algorithmic result is saying, given a polynomial from such a circuit class, I can output the factors. An even stronger algorithmic result would be, given a polynomial from a circuit class C, we can output a representation in the same circuit class for each factor of the input polynomial. Something like this can only be expected if you first have the structural result. Now, this is just a quick recap of what Shantanu presented, which is that we now know a result of the following form. Suppose f is some degree d polynomial with a size s and depth delta circuit or a formula. Then with just a small blow up in the depth and some blow up in the size, you can obtain circuits or formulas for the factors as well. So I hope this structural result is clear. So once you have that, this is the main algorithmic result. So fix any constant delta of your choice. So then I can give you a deterministic algorithm which runs in sub-exponential time in the number of variables, degree, and so on, which takes as input some circuit of size s and depth delta of degree d, computing a polynomial of degree d, and it outputs for each irreducible factor a size poly sd circuit, and the depth only goes from delta to delta plus some constant which is independent of everything else. So maybe delta plus 10 or something. So I hope the result is clear. It's essentially an algorithmic version of what Shantanu presented. Right. So it crucially builds on these structural results. So at this point, the audience would be curious, why constant depth circuits? And why sub-exponential time? I mean, can't you do better? Because in randomized algorithms, we do know polynomial time algorithms for getting circuits. That was Kaltofen's algorithm. So why sub-exponential time? Sort of one word answer is polynomiality testing. Okay, but before we get to that, just a very quick overview of what these factorization algorithms look like. First, you pre-process the input polynomial. So if you remember, Shantanu said that you'd like to make sure that the polynomial is monic, and the polynomial, when you accept one variable, if you make all the other variables set to 0, then it should be square free. These were some sort of starting conditions for you to be able to apply the structural result. But once you're trying to do something algorithmically, you want to know how to do this. In general, the algorithms do this randomly. You can do something randomly and you get this. I'll get to what that is. But we'll have to do this deterministically. Then the second step is to compute these approximate roots, which is really what Shantanu covered. How to use Furstenberg's identity to start from some constants and build approximate roots. And then the final step is to recover the true factors. So this is sort of the main new de-randomization step in some sense. The second step of computing roots, which Shantanu covered, is completely deterministic. The first step requires some de-randomization. All right. So let's get to the part of so this is mostly what Shantanu covered, but I'll sort of give a quick overview of how it shows up in the algorithm. So the simplest case here is going to be not necessarily looking at factors, but roots of your input polynomial, which is a special case really. So suppose f can be factorized as g1 times g2, blah, 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 till gk. Let's just focus on a case where hx is some polynomial such that if you replace hx in the place of the y variable, then this becomes 0. So hx is a root, right? And if hx is a root, using sort of this high school algebra, you can see that y minus hx is a factor. So this is really a special case of factors. Okay. Now, if f of x comma hx is 0, then f of 0 comma h of 0 is also 0. Oh, that there should be is equal to 0 there. So h of 0 is a root of f of 0 comma y. So how can you get your hands on this h of 0? You can take the univariate, which is f of 0 comma y, and apply the Loesch-Lenstra algorithm or something and compute h of 0. And now you can use Furstenberg's identity, which Shantanu showed, to extend it to the complete root h of x. This is something I won't dwell over further. And the important part here is that if you use this identity, then you will get these size and depth bounds that we care about. Now, in general, a polynomial might not have a y root because it might look like y square minus x1 times y square minus x2. There is no y root. But if you're sort of brave enough, you can get y roots which are Puzzio series, which are sort of like power series, but you allow negative and fractional exponents. This really won't matter much in the next slide. But just for an example, y square minus x1, you can write it as y minus square root x1, y plus square root x1. What's important here is that if you do a random shift of your variables, then you do actually get a factorization into power series roots. So this is something that's sort of building upon what Shantanu said, that we can factorize our polynomial into power series roots, compute those power series roots approximately, and then combine them to get the factors. So this is just saying that if you do a random shift, then you can actually expect something like this to hold. Okay, so now we have a polynomial f, and assume that we have done a random shift. This is important. Later we'll have to say how to de-randomize this, but assume we have done the random shift. So all these phi i's are power series roots. each power series is an infinite object. But what I'll do is I'll set the x variables to 0 and then just get my hands on each of those constant terms that starts off those power series. I can do that using univariate factorization. And then I use the Furstenberg identity to compute each of these roots approximately. Right? Okay, so now we have these approximate roots. Now the question is, how do we find the actual factors? And the real issue here is we had some irreducible factors, right? G1, G2, and so on. And each of those GIs was made out of some product of yi minus phi's. So it was all made of some roots, but I don't know which roots go together. Which of these roots are conjugates of each other? Okay, so that's one sort of algorithmic question which I think Roshan asked at the end of the talk. And the final thing is, all of this works after a random shift of variables. How do you find such a shift deterministically? So finding the right shift deterministically, it requires a quick detour through polynomial identity testing, which again, Robert covered it in great detail, but I still quickly just go over this. The PIT problem is just, you're given some polynomial, let's say some succinct access to it, like a circuit, and you just want to query it and figure out, is this circuit computing a non-zero polynomial or not? And the easy randomized algorithm is to just sample enough random points and check. And this works due to the Schwarzschild lemma. And this is efficient for poly-sized arithmetic circuits as a randomized algorithm. And it's a big open problem to try and make this deterministic, and it has connections to finding lower bounds and so on. So for us, one way of trying to get this a deterministic algorithm is a hitting set generator. And what's a hitting set generator? It's a tuple of polynomials. And what is the guarantee that these polynomials give you? Well, one hope is that the number of variables w should be much less than the number of variables x in your initial polynomial. And for any polynomial in the class C that you care about, if it was a non-zero polynomial, then plugging in this hitting set generator, composing it with the polynomial should maintain non-zeroness. Is there a chalk? I think just the easiest way to visualize this is you had some f, which had some input variables. Now, I don't need to think of it as a polynomial and on a huge number of variables. I just have a smaller number of variables. This is the hitting set generator. And if f was non-zero, then f composed with this is also going to be non-zero. So in some sense, if you just go over all these tuples that you get by taking elements from this smaller bunch of variables and just iterating over the hitting set generator, that's a hitting set. The real takeaway from this slide, even if it's a lot of things in one slide, but the main thing is a hitting set generator reduces the number of variables while maintaining non-zeroness. Right? Okay, so now we had this initial shift that we had to do. Now we want to know how to do this deterministically. The main idea is that if your input polynomial has a small constant depth circuit, then there are some related constant depth circuits such that if you can find a non-zero for those, then you can use that as the right shift, right? Okay. One such important polynomial that shows up here is the discriminant of f. For example, in high school, we've seen that for quadratic polynomials, this b squared minus 4ac is the discriminant. This is in some sense the same thing generalized. And there's a result by Robert and Avivik Durson, which shows that the discriminant of constant depth circuit turns out is also a constant depth circuit. And it's a really interesting result. But this is important for us because recently there have been some breakthrough results, which again, I won't explain the whole series of results, but I'll just say that right now we do have sub-exponential time deterministic PIT algorithms for constant depth circuits. So this answers the first question of why does our algorithm only work for constant depth circuits and why is it sub-exponential time? Because in some sense, the reduction is to PIT. And the best algorithms that we have for PIT for constant depth circuits are sub-exponential time. And for larger classes, we do not have unconditional, non-trivial PIT algorithms. Right? Another result that Robert mentioned is that there is another hitting set generator for constant depth circuits. Now, the point is you can use either of these hitting set generators or PIT algorithms to find points where these polynomials that we cared about, they take a non-zero value. And this will give you a good shift deterministically. So this is for the last point. Okay, so now what's left is which roots came from the same factors. So I see that I have about 5 minutes left. So I might skip something, but I'll be happy to answer it offline. So finding the right combination of roots to form factors. Okay, what's the setup? We have a polynomial f of x comma y, and we have factorized it as some power series roots, product over I, y minus phi x. These phi's are, per se, they are infinite objects, but think of them as just some approximations, truncated to some degree. And our goal is to find out the right subsets of these roots, which together form factors. Now, in some sense, we do know how to do this, but it's not efficient. There is some brute force way of doing this, but it's not efficient. So the question is, what if we can somehow reduce the number of variables while ensuring that the factorization pattern remains the same? For one thing that we saw is that there are some things where we can reduce variables while maintaining some key property. For example, hitting set generators reduce the number of variables while ensuring that polynomials from a certain class remain non-zero. What we are trying to say is, instead of non-zeroness, can I somehow reduce the number of variables while maintaining the factorization pattern itself? Because that's really what I'm trying to capture by saying which are the right roots to combine. Now, if I can somehow reduce the number of variables while maintaining the factorization pattern, then I can use even an inefficient algorithm to sort of obtain what the right combinations are. And then I can use the Furstenberg identity to combine the right roots, to compute the roots and then combine them. So the combination is something we saw in Shantanu's talk, which is just take the product of y minus roots. Okay. So this is, in some sense, the main lemma underlying the algorithm's correctness, which just says that if you take any hitting set generator that preserves the non-zeroness of constant depth circuits, then it turns out that it will also preserve the factorization pattern of constant depth circuits. And the proof ends up telling us that this is true for any rich enough class of polynomials. All you need is some sort of closure result to hold for power series roots, which is what we saw in the previous talk. So yeah, this is the main sort of lemma. I am not sure I should really go much more into the proof ideas. Maybe I'll just say a couple of lines, which is that there is a way to capture. Okay, what do I want to say? So what do I want to do? I want to somehow reduce the number of variables while maintaining irreducibility. It turns out that you can capture the irreducibility of a factor using some sort of divisibility conditions. And so that's the first step. And the second step is that you can capture divisibility conditions using non-zeroness preservation conditions. In some sense, PIT conditions. So there's two steps of reduction. You can go from irreducibility to divisibility, which I skipped. And then you can go from divisibility to PIT, which I will also skip, but I did have slides for it. But both of these are, they're technically not hard conditions, but they are really at the heart of why this thing works. Okay. But okay, let's just have a look at the final sketch of the algorithm. So the first step is that you use this deterministic PIT algorithm, pick your favorite among the two that we know, and find a good shift using those algorithms. Now then apply a hitting set generator. Again, I mean, the deterministic PIT algorithm and the hitting set generator, they are essentially the same things for us. So you can apply that, go to a world of smaller number of variables, factorize it. That tells you what the right combinations of starting points are. Now, from those starting points, you can use Furstenberg to get the roots, and then you combine them. So you compute each approximate power series root via Furstenberg and take the appropriate products to output factors. So, okay, so that was the final sketch of the algorithm. Some interesting future directions. Okay, here we saw that you can reduce irreducibility testing to first divisibility and then to PIT. But there is a distinction between black box PIT and white box PIT, which maybe I can talk about it offline. But if you are in the algebraic complexity world, this would make sense to you, and then this is an interesting question. One easier to state question is, if these are not constant depth circuits, if these are even simpler, if they are sparse polynomials, which are depth 2 circuits, then can you get better running time for this? That's not clear. Right now, I mean, by virtue of our algorithm, you do get sub-exponential time algorithms, but it's possible that you can do something better. And there's something else that Shantanu mentioned when he was asked about doing this over small characteristic. This is the simplest question that we don't know the answer to. Can you say something structural or and then also algorithmic about the pth root of a polynomial over characteristic p? So yeah, key takeaways. We have a deterministic sub-exponential time algorithm, takes constant depth circuit as input and outputs small constant depth circuits for all the factors. Furstenberg's identity allows us to compute efficient representations for approximate power series roots, which you can then combine for factors. And the main lemma is that a hitting set generator, which only is guaranteed per se to maintain non-zeroness, also maintains factorization pattern. Thank you.
Questions? If there are no questions, then we can.
Sorry. Going from divisibility to PIT or irreducibility to PIT? Yeah, it's not too hard. So. Right. So essentially the idea is, suppose some factor is made out of, let's say, phi1, phi2, phi3, right? Y minus phi1 times y minus phi2 times y minus phi3. Suppose this is an actual factor. And what you want to do is somehow reduce the number of variables while ensuring that exactly this combination is a factor and no subset. I mean, it is possible that once you reduce the number of variables, suddenly just y minus phi1 times y minus phi2 has become a factor by itself. So we just want to ensure that that does not happen. So what does that mean? We want some transformation reduced such that some subset of roots form a factor, which is a divisibility condition, that A divides B. This product is a factor of the original polynomial. That's a divisibility condition. And we want to say that is a factor if and only if once you do the reduction, now you take product over those roots of y minus the reduction of those roots. So the initial combination is a factor if and only if the post-reduction combination is a factor. So this is what we want out of our transformation. And because this is a divisibility condition, we can use what was on the next slide, which is that this divisibility preservation, now you can reduce it to non-zeroness preservation, and then you can use PIT. I have a question. When do we leave for dinner?
I think 6. Thanks for. Okay, let me answer the question. We're going to dinner to the restaurant Global Fusion at Worli.